So what we're going to do is we're going to look at how our five factors relate to our collision theory. Now remember last day we talked about collision theory, which explains that a reaction occurs when particles collide with each other with enough energy and the correct orientation. And we also looked in general how each of the factors might affect either the energy of the collision or the number of collisions that are effective, i.e. they would make sure that they have correct energy or sufficient orientation. So what we're going to do is we're going to go through a number of demos. We can watch the demos, and then we'll talk about how that demo exemplifies how that factor would influence the reaction. So here we have our concentration in our first beaker. On the left, we have 1 molar acetic acid, and on the right, we have 3 molar acetic acid. We have equivalently length pieces of magnesium strip. And if we now combine them, we can see how they react with each other, and we can see this that the strip in a 3 molar each acetic acid will be reacted much quicker. We can see that rate of bubble formation in the 1 molar it's slower, but in the 3 molar it's much faster. And it's already all consumed in the 3 molar. So as we said, collision theory says that my rate is proportional to my concentration. So what this says is that my concentration goes up, my rate of my reaction goes up. But the question is why, and how can we use our theory? Well, we know that concentration is the number of particles we have in a given volume, and the more particles I have in that volume, the more collisions I can have. And so therefore, at higher concentrations, I have more collisions, which means that there will be more chances for the particles to collide. What about temperature? So here we have a series of beakers where I have magnesium pieces placed in an acid, and the acid is in different water baths. So when we first start this, the beaker on the left is in a cold water bath, whereas the beaker on the right was in a room temperature, and this is a hot water bath. And as we can see, as we increase the temperature, the rate of the reaction increased. Okay, now, so again, collision theory. So as a result, we can say that my rate is proportional to my temperature. We know that temperature is a measure of the motion of the particles. The higher the temperature, the more kinetic energy, so the more movement particles have. So this leads us to the first way in which a change in temperature can affect our rate of reaction, because we said that when we looked at rate being a function of number of collisions times fraction of effective collisions, we said temperature would affect both the number of collisions and the fraction of effective collisions. So therefore, at a higher temperature, my particles are moving more. This increased motion will allow for a greater number of collisions. So this is the first way in which my temperature could affect the rate of reaction. But how does it affect the fraction of effective collisions? To understand that, we have to use what's called a Maxwell-Boltzmann curve. Now, Maxwell-Boltzmann curve shows the distribution of particles in a sample of matter with a particular kinetic energy. Okay? And so here we have in our graph, we have our kinetic energy distribution, and this would be the distribution of particles with a given kinetic energy in a sample of matter. Okay, and we can see our different values. We find most of our values are close to our average temperature, i.e. near the peak of the curve, but there are some particles that are moving really slow and some particles that are moving really, really fast. So now if we were to take this, one of the things we know is that for collisions to occur, they have to have a minimum amount of energy. So I could show where this minimum amount of energy for a collision to be effective occurs. And so we could add this line. And this line is what we call our threshold energy, or could also be referred to as our activation energy. Okay, it's the minimum energy that a particle needs for effective collision. Well, if we look at the area under the curve in this region, given that area represents the number of particles, we can see that only a small number of particles have sufficient energy for an effective collision. Okay. What if we were to change the temperature? Well, if we were to change our temperature, it would give us a second curve, and you'll notice that the total area under the curve doesn't change. All we do is we shift it and spread out our number of particles. Okay, and so the red line represents a second temperature, which is higher than my first. Well, in this case, we can see that we have a much greater number of particles which have enough energy for an effective collision. Okay, so at our lower temperature, the number of particles with sufficient energy for an effective collision, represented by the red, is relatively small. Whereas at our higher temperature, the number of particles, as represented by the green, is much higher. So since we have a greater fraction of particles with enough energy for effective collision, this means that my percentage of collisions that will be effective will go up, which will increase my rate of my reaction. Okay, so as we know, temperature is proportional to our rate. Okay, so collision theory can also explain the impact of increasing temperature by saying that there will be more particles with sufficient energy for effective collision, which will increase our rate of our reaction.